Hi, welcome to this talk. Today we're going to talk about Do More with RedisGraph 2.2. My name is Peter Caillot. I'm the product manager of RedisGraph, and today I'll be co-hosting a talk with Roy Lippman. Roy Lippman is the creator and also the lead engineer on the RedisGraph project. RedisGraph 2.2 is not yet GA, but we're happy to announce that there is a release candidate available. And today we'll talk you through what kind of things you can do with RedisGraph and with this new version. First, I'll start with giving a brief introduction about what RedisGraph is and what we do in the past year, so we can do more with Cypher. And then I will hand it over to Roy. Roy will dive into the details, into the technical details about RedisGraph, how the traversals effectively work. And then he will also talk about two new topics or features that we added. So we allow you to do query optimizations by having a slow log available and also query profiling. But we also did performance optimizations. For that, we'll talk about how the query cache inside the new version works. And then lastly, Roy will also cover what's new section or what's next section, what's upcoming into the next releases. First, I want to show you this chart. This chart is taken from dbengines.com, and it effectively tracks the popularity changes across database management systems. And since 2013 till now, effectively, we can see that graph database management systems are clearly going through the roof. So if that is not enough of a teaser to get you looked into RedisGraph, I'll tell you what a graph database effectively is. So a mathematical graph is effectively a collection of vertices and edges. So now when we talk about RedisGraph effectively adheres the property graph model. And there effectively we have four building blocks. There are nodes, relationships, labels, and properties. So to give you an example what they are, so the vertices from our mathematical graph, they become nodes. They're represented by the circles. The edges are transformed into relationships, and they represent obviously the arrows. Labels are attached to nodes. So here we can see that there is on the left, there is a node that has a label database. There's also a label query language and a label company. Nodes can have 0 or multiple labels. Relationships, they always have exactly one relationship type. So we can see that there's a relationship of the type supports, and there's a relationship of the type written by. Both nodes and relationship, they can have properties. So properties effectively is a key value map or a dictionary. So we can see that the node on the left has a property with a key name and a value RedisGraph. And there is also a property on the relationship supports, which is from 2016. So you can look at this graph that RedisGraph is supporting Cypher, which is a query language for graph databases since 2016, and has been written by Redis Labs. So what is a graph database? So a graph database is a database with a graph API. So it's a query language that allows you to query, in this case, a property graph. I do want to add on top of that there are also graph native databases, and graph native databases are graph databases with also an index-free adjacency. So, which means that if you want to find the direct neighbors, you have a time complexity of O1 instead of O log n. So you don't have to do any index lookups to find your neighbors. You can just chase pointers. How are we doing this inside RedisGraph? There are two ways effectively to solve this. There are adjacency lists and adjacency matrices. We chose the adjacency matrix approach, which kind of like allows us to use state-of-the-art libraries. What is an adjacency matrix? In an adjacency matrix, both the rows and the columns, they represent all the nodes within your graph. And in this case, there is a 1, for example, on row 1 and column 2, which indicates that there is a relationship in between node 1 and node 2. Now, when your graph tends to get very large and you have effectively relatively little relationships, we would have a sparse matrix. Now, sparse matrices are easily compressible. And it was until recently when there was a couple of professors, they created a library, or they made an API definition called GraphBlast, which allows you to do linear algebraic operations on top of these compressed sparse matrices without having to uncompress them. That effectively made it possible to do RedisGraph. So we're using SweetSparse, which is it's just an implementation of GraphBlast under the hood of RedisGraph. So what have we been doing going from RedisGraph 1.2 to 2.0 effectively to 2.2? 2.0 was released in January, and 1.2 was effectively released last RedisConf. I want to show you the progress we made effectively in the support for the Cypher query language. So you can do more with Cypher. One way to look at it is, for example, is that the LDBC. The LDBC is the industry reference as a benchmark system for graph database systems. So we can see that we now, in this latest version, we support up to 80% of the test cases. Cypher also comes with a TCK, with a toolkit that allows you to validate how much of the Cypher query language we support. But you can also see there is a clearly upward trend because each version of RedisGraph, we do a clear investment in supporting more of Cypher. To allow you to do more and to allow more use cases to be supported by RedisGraph. Our ecosystem is also growing. Last year we had 7 drivers that allowed us to connect to RedisGraph. We doubled that effectively in a year. And there are also some GitHub projects that are looking at an integration of GraphQL combined with RedisGraph as a backend. In the 2.0 version, we also added a full graph response. So we were now effectively returning nodes and relationships and paths as full entities. And that allowed us to do graph visualization. Redis Insight is our own developer tool, or a tool for developers to work with Redis. And it has its own RedisGraph tool inside Redis Insight. And I will give you a short demo about that afterwards. But we also have 2 partnerships. One is with Linkurious, the other one is with Graphql. Linkurious effectively created a graph intelligence platform which allows you to do fraud or financial investigations on top of a graph database. It also leverages Redis Search. Graphql allows you to build graph applications as a graph, right? And we also have an integration there with Redis Graph available. So here is a small demo of how the Redis Graph integration looks inside Redis Insight. So we're just looking for an actor here in a database that is linking actors in movies. And then once we double click on a node, we will effectively fetch the direct neighbors of that node. We can also go into full screen mode and further explore the graph. So you can go ahead and you can download Redis Insight at redislabs.com/RedisInsight. And lastly, I want to leave you with some use cases, what Redis Graph would be good for. Typically, Redis Graph fits all the common graph use cases that are out there. So social recommendations, customer 360, but also fraud, master data management, and resource management. We have several customers effectively that are using Redis Graph for identity and access management type of use cases. But what I want to leave you with is kind of like an abstraction of that instead of going to the details of each of those use cases. So if you would have a project, a software project, and you would like to understand if Redis Graph is a good fit, there are 4 dimensions, and if you have all 4 of those, then yes, great, go ahead. It's a very strong reason to choose for Redis Graph. The more you have, the stronger the case comes. It still doesn't mean that you shouldn't use Redis Graph, but the more of those dimensions you score high on, the higher it would be the best tool inside your toolbox to use for solving your problem. So the first one is that is your database, is your data transactional? So is this a static graph where you, for example, model data that doesn't change over time, or is the data effectively changing continuously? So do you effectively need a database management system? Is your application effectively real time waiting for the response? Do you need a fast response time for answering your complex graph queries, or can they be asynchronously processed? It's kind of like the differentiation between fraud detection and fraud prevention. Is your application being built in an agile manner? Graph databases are schemaless, so you don't have to define the full schema up front, which means that you can start with a simple schema and parts of your dataset and let it grow and evolve over time. Graph databases lend themselves very easily to do so. And the last one is does your use case have complex queries? So do you need to do deep graph reversals, such as a depth first search or a breadth first search, or you need to combine several entities when you're validating a single node, you want to combine many of its neighbors, then the fact that you're using a graph native database will really benefit you a lot. And with that, I would like to hand it over to Roy Lippman, the creator of Redis Graph.
Hi everyone, I hope you're all doing well. I wanted to go over and show you some of the new additions and new features that we've added to Redis Graph with this latest version. So just to make sure that we're all on the same page here, let's just go over the fundamentals on how a graph object is being represented within Redis Graph. So we're using what is known as sparse adjacency matrices to represent our graphs. So you can think about a matrix as just a big table with rows and columns. And suppose that we have this very simple graph where we have node I, which is connected to node J. We can represent this graph in a matrix by saying that the row I of the matrix and column J of the matrix, basically specifying the ij entry in the matrix to have the value 1 in it. And so you can think of at the row of the matrix as the source nodes and the column of the matrix as the destination nodes. So row I, column J has a 1 in it, meaning that some node with ID I is connected to, and this is a directed connection to some other node with ID J. So within Redis Graph, we have different type of matrices. We have what we refer to as the adjacency matrix, and this matrix basically just captures the overall structure of the graph. It doesn't care for labels that you can attach to nodes. It doesn't care for edge types, relationship types. It just cares for, is node I connected to node J somehow, regardless of the node labels and the edge types, then okay, set entry ij to 1. We also have what we refer to as label matrices, and basically we have one label matrix for each label in the graph. So suppose that your graph has two different type of entities, let's say nodes representing people and another set of nodes representing cities, then you basically have two different labels, person and city. And each one of those has its own matrix. These type of matrices are diagonal, so if node I is labeled as a person, then the label matrix for person would have an entry set at position I. Lastly, we have relationship matrices, and these matrices basically captures connections between nodes, and these connections have a type. So you can say that some person I has visited some city J, then you have a connection of type visit. Therefore, we would have a visit relationship matrix. And so if I visited J, then the ij entry within the visit matrix is on. Now, this is just to illustrate label matrices. So once again, I is labeled as L, then we have a label matrix L with entry II set to 1, and once again, the label matrices are diagonal. Now, one of the key operations that you want to do with graphs is basically to traverse them. And so with matrix representation of a graph, you can traverse your graph by performing matrix multiplication. So here's just a quick example. Suppose this is the graph that we're working with. We have nodes I, j, and k. I is connected to j with an edge of type r. J is connected to k with an edge of type s. So we have two relationship type matrices, R and S. And if we wanted to see to which nodes I is connected to after performing two hops, then we can just simply multiply the S and the R and S matrix to find out. And suppose that we did that. So here's the RS matrix, standing for the multiplication of matrix R with matrix S. And we can see that we have an entry at position I, K, meaning that after performing two hops, we found out that node I is basically, node I can reach node K after performing those two hops. And this is how Redis Graph basically performs traversal. So let's look at a more realistic example. Suppose that we want to find out some person A, or I should say all of the persons A, which have called some other person, let's call that other person B, and we want to make sure that that B person owns some account Z. And let's say that we're only interested in either or both the A nodes and the Z nodes. And so what Redis Graph would do when presented with this pattern, it will compose an algebraic expression, a set of matrix multiplications. In this case, we would multiply the person matrix with the call matrix times the person matrix once again, times the own relation matrix, and end up with multiplying with the account label matrix to end up with a result matrix, which would tell us which A persons satisfy this pattern and will eventually reach this Z account node. And so up until this new version of Redis Graph, we were using just a simple array to represent an algebraic expression. Each entry within the array would stand for an operand, basically a matrix, and we would just scan through the array, performing the multiplications left to right to compute the expression. The problem with such a representation is that there's not too much space for expressiveness. It works well for the simple case, but Cypher, the query language, allows you to specify more complicated traversal patterns. So let's just list them. We have the directed pattern, which can go either left to right, but can also go right to left. You can also specify patterns where you simply don't care about the direction, so undirected, directed, agnostic patterns, in which you just omit the arrow sign. You can have multiple relationship type within a given edge, so you can say that I want to traverse on either relationship K or edge type J. Either one would suffice. And lastly, we can have variable length hops or patterns where you say go from A to B, but perform 3, 4, or 5 hops. Either one would suffice. And so the array representation simply doesn't have enough expressiveness to work with such different traversal patterns. So here are a number of examples and the algebraic expressions that we were to compute for them. So here we're looking for a player A, which is a member of some team. Let's call that team T. And once we found a team for A, we want to find other players on that team. And know that this pattern specifies traversals in both left to right, going from A to T, left to right. But then it also specifies traversal in the reverse direction, B to T, going right to left. And in such situations, we will transpose one of those relationships. So in this case, we can go from A all the way to T by performing player times member times team. But then if we want to continue on from that team to player B, we need to transpose the member matrix. Another example would be a direction agnostic traversal, where we want to take into consideration more than one relationship type. So in this example, we want to find if A is connected to B or the other way around. Well, inspecting both the works and study relation. Translating that into an algebraic expression, we get works plus study. So by adding those two matrices together, we're basically taking into consideration both relationship types. And then to make this algebraic expression direction agnostic, we add the transpose of that addition. And whenever you're adding a transpose of a matrix to itself, you end up with a symmetric matrix. So just as an optimization, we can focus on either the upper triangular form or the lower triangle form of the matrix and drop all of the other entries, because this is once again a symmetric matrix. And so we've switched from an array representation into a tree-based representation of an algebraic expression. The tree itself has two different types of nodes within it. The nodes colored with orange are operation nodes, and we have operations such as addition, multiplication, and transpose. The leaf nodes, colored with blue, are the actual operands, the matrices on which the operation operate on. And so this is just the last example of traversals. And here we want to find some node A, which is connected via a relationship type I, performing two hops here, and then reaching B, and we want to see if that B has a C node connected to it with either the J or K relationship type. And so to translate that to an expression, we get I to the power of 2 representing those two hops from A to B, but then we multiply that by the transpose of J plus K, following our last example. And so we can apply the matrix addition and multiplication rules and expand this expression. So we can move the transpose in and apply the transpose to the individual operands within this summation. And so this becomes I to the power of 2 times, and then within parentheses, transpose J plus transpose on K. And then we can go ahead and expand that even further by applying the multiplication over the addition. And so this becomes I to the power of 2 times transpose J plus, once again, I to the power of 2 times transpose K. And as a last step, we can choose which multiplication we want to perform first. So we can do I times, and then within parentheses, I times transpose j, plus I times I first, and then multiply by transpose k. And so we might look at some expression and then expand it to hopefully reach an expression which will be cheaper to compute. Let's look at a new feature that we have added, which I think is native to Redis, which is this slow log. Basically, suppose that you have an application which queries your graph database, and you're issuing different queries. You can use the slow log to get a list of your 10 slowest queries, which you might want to inspect, and maybe you would like to optimize those queries. And so one thing to note here is that the slow log is attached to a graph. So in case you're running multiple graphs, then each of these graphs that you're running would have its own slow log. And so to get the slow log, you just call graph.slowlog, and then you specify the graph key that you want to get the slow log for. The result would be an array of 10 entries, one for each query, if you indeed have 10 different queries. And each entry is composed of 4 different fields. The first one is just a timestamp in which the log was taken. The other one is the command that was executed. In most cases it would be graph.query. Then the query itself, and lastly, how much time did it took that query to run. Alright, suppose that you've investigated your slow log and you have identified a query which is not running as fast as you might have expected. One way to further investigate is to run a profiling against that query. And you can do it with the query profiler. Now, just before showing you how does a profile query looks like, it's important to understand that whenever Redis Graph is presented with a query, Redis Graph would create an execution plan. And basically an execution plan is a set of steps that Redis Graph will follow, and at the end it would have the result for the query. And this is just a simple example. Basically the query asks for any 2 nodes that are connected to one another. The results that should contain those 2 nodes, and we're only interested in 3 pairs. And so given that query, the execution plan that Redis Graph would construct is composed of the following operations. The first one is an all node scan, which would basically scan through the entire nodes, all of the nodes in your graph. So for every given node, the conditional traverse, the second operation, would perform a traversal, a one hop in this case, traversal to reach the set of neighbor nodes. And lastly, we have the result operation, which will produce the result set. We're missing the limit operation here because I didn't have enough space. And so this is just a breakdown or basically the plan that Redis Graph would execute given a query. Now with the profile, you're also getting the execution plan, but now the execution plan is being enriched with some additional information. So each operation on your execution plan is telling you exactly how much time did that operation executed. In addition, operations use what we refer to as records to pass information from one operation to another. And so in addition to the amount of time each operation spent executing, each operation will tell you how many records it managed to produce and pass on. Alright. Lastly, I want to introduce the query cache, which is also a nice addition in this version. And so, just an overview of what happens when a query is presented to RedisGraph. There are a number of steps that are obviously taken. The first one builds what is known as an abstract syntax tree from the query string representation. Next up, once the parser was able to produce an AST, that AST is passed through a set of validations, making sure that not only the query is well constructed, but also that it passes a certain set of validations. Once the AST or the query passes those validations, we can go ahead and construct an execution plan for that query. The execution plan is then further optimized. And lastly, we evaluate the execution plan, and compose the result set. Now, suppose that a query comes in. It is not cached yet. It might be just the first query that you're issuing. And so that query would go through all of those 5 steps that we've just seen. But we will also cache this query. And by caching a query, I mean we would relate the string representing the query with the execution plan constructed for that query prior to optimizing the execution plan. And so if you reissue that query, then if it is found in the cache, we can skip the parse, validation, and execution plan construction phase and just get the cached execution plan, optimize it, run it, and produce your result set. Now, the query doesn't have to match itself exactly. If you are using parameterized queries, then we disregard the parameters. Meaning that, let's look at this example, for instance. Match n, find any node in the graph where n.v, the node n has an attribute v of type $v, where $v stands for a parameter. In this case, the first query, $v equals 1. Now, if we issue a second query, which basically is the same query, but we've updated the value of the parameter, we would still get a cache hit from the query cache. So this is just another reason why you should use parameters for your queries. With that, I would like to just talk a little bit about what is on the horizon for us. So the first feature or enhancement that we would like to address is log-free writer. Currently, RedisGraph would run multiple read queries all in parallel. You can even have a single writer running in parallel with those read queries up until the point where the write query is actually modifying when it is committing the changes that it wants to apply. At which case, the writer would have to acquire a write lock, which means that no reader can execute. And so with a lock-free writer, we can have both multiple readers and a single writer all running concurrently without any contention. The second feature that we want to introduce is an enhancement to our matrices representation. Currently, all of our matrices are what I refer to as flat matrices. Block matrices is a different representation or a different way of looking at a matrix. You can think about as a matrix, a flat one, being subdivided into sub-matrices, and this should allow us to do some better parallelism over our matrix operations, but also it will allow us to update our matrices much faster when if a connection is formed or a connection is removed. The third one is bulk update. We have a utility to load a new graph fast into RedisGraph, and so the current utility would only allows you to quickly insert new graphs. You cannot update an existing one, and so we want to extend the support for the bulk insert operation to also support bulk updates of an existing graphs. Obviously, we want to extend our support for data types, and so we have a number of requests which we want to address with regard to the map data type, but we also want to include the geo data type. And lastly, we want to extend our classic algorithm package to include algorithms such as connected component and community detection and single source shortest path. And with that, I want to thank you all for joining us and listening. Stay healthy, stay safe.